Hi, welcome to the lecture of Ofdm and Fbmc, which is filter bank multi-carrier modulation. First, we talk about Ofdm, which is basically orthogonal frequency division multiplexing. Ofdm is basically the current dominant technology for broadband multi-carrier communication. It is widely adopted because of a number of advantages, namely orthogonality of subcarrier signals, which enables 1. Trivial generation of transmit signal through an inverse fast Fourier transform, trivial reception of the transmitted data symbols through a Fourier transform, fast Fourier transform, trivial equalization where typically one complex value is there per subcarrier, and trivial adoption of different multiple input multiple output schemes. Second, closely spaced orthogonal subcarriers partition the available bandwidth into narrow subbands, and also simplified carrier and symbol synchronization due to the special structure of your Ofdm symbols. However, in certain applications like cognitive radio and in the uplink of multi-user multi-carrier systems, where a subset of subcarriers is allocated to each user, Ofdm may be an undesirable solution. In this lecture, we look at some of the shortcomings of Ofdm and conclude that Fbmc, which is filter bank multi-carrier modulation system, could be a more effective solution in certain situations. To do this, we first need to return to the basics of Ofdm and formulate equations that apply to both Ofdm and Fbmc. Basically, the main drawback or the main problem comes in the Ofdm due to the side lobes of each subcarrier. Here, the side lobes of each subcarrier are very few dBs lower than the main lobe. This frequency response is basically created by the filters associated with the synthesized subcarrier signals at the transmitter and the analyzed subcarrier signals at the receiver. It may not be apparent at first, but an Ofdm transceiver uses rectangular windowing functions to transmit or receive an Ofdm signal. So we'll slowly develop on this and see how this windowing function comes into the picture. So let's start by looking at a typical Ofdm transmitter block diagram. Okay, so if you take the Ofdm transmitter block diagram, we can see that Ofdm symbol is basically the sum of multiple modulated exponential subcarrier signals. However, where these signals are basically orthogonal, right? So where does the orthogonality between these subcarriers come from? Orthogonality, or in other terms we call the inner product equal to 0 between two exponential signals, the definition for which is given by the inner product of e power j 2 pi fkt and e power j 2 pi fit conjugate is given by 1 by t integral over 0 to time t e power j 2 pi fkt into e power minus j 2 pi fit dt. Okay, for clarity, let's replace capital T by T symbol, which is basically your symbol duration, and let's see how we can actually nullify the equation. So replacing the symbol, we get 1 by T. The right hand side of the first equation is equivalent to 1 by T symbol of integral from 0 to T symbol e power j 2 pi k t divided by T symbol minus e power j 2 pi k t divided by T symbol into e power minus j 2 pi I t divided by T symbol dt, which is nothing but 1 by T symbol duration times the integral over a symbol duration e power j 2 pi k minus I t divided by T symbol dt, which is like is equal to 1 if k equal to I, else it is 0. Right, in other words, the exponential are orthogonal if both frequencies are an integral multiple of the fundamental period t symbol. But there is another important observation to make. The orthogonality holds only in an integration interval of t symbol length. Okay, this observation can be illustrated by the formula 1 by t symbol is equal to integral over t symbol e power j 2 pi k minus it divided by t symbol dt, which is nothing but, which we can equivalently represent it as minus infinity to infinity a function pt of t into e power j 2 pi k minus I times t divided by t symbol dt, where we define pt of t as equal to 1 if my small t lies between 0 to symbol duration, else it is 0. So basically we can conclude that there is some sort of windowing that is happening. Okay, the difference between Ofdm and Fbmc basically lies in the choice of the filter pt of t, which is commonly called as the prototype filter. Since each subcarrier needs to be filtered by this prototype filter in Ofdm, we can modify the transmitter block diagram accordingly. So if you see this transmitter block diagram, we can conclude that Ofdm is basically a sum of windowed modulated exponential functions, and since the Fourier transform of a rectangular pulse is basically a sinc function, side lobes as previously shown are created for each subcarrier in Ofdm. Okay, now before moving to Fbmc, we need to find a parallel for the receiver, right? So moving on to the, okay, before that, if you want to see, we can conclude that given by this equation, Ofdm is a sum of windowed modulated exponential functions, right? Where x of 0, x of 1 are the symbols modulated by the exponential functions and filtered or windowed by the pulse shaping or the rectangular pulses pt of t. Right, now at the receiver we can observe that we need to first separate one subcarrier from the other for symbol extraction. So what we do is basically we multiply the received signal y of t by the conjugate of the subcarrier that we want to extract, by the fact that subcarriers are orthogonal between each other. The conjugate of the subcarrier, which is e power j 2 pi f naught t, is orthogonal to the other subcarriers except for e power j 2 pi f naught t, and so on and so forth for the other subcarriers. But again, the orthogonality basically holds only in a specific interval of time of length t symbol, which means that at the receiver we have a prototype filter PR of t that is also rectangular pulse of the length t symbol. So if you observe the diagram, we find a prototype filter pt of t at the transmitter, and we find a prototype filter PR of t at the receiver. Right. This receiver block diagram is basically valid for both Ofdm and Fbmc systems, and the basic difference lies in the choice of the prototype filter pt of t and PR of t and the symbol spacing t. Right. Now we are basically bringing a new symbol called t, or new variable t, into the discussion. From the beginning we worked with a variable called t symbol, which we call as the length of an Ofdm symbol. Right, as you remember, in practice the actual length of an Ofdm symbol is not just the t symbol. We add something called as cyclic prefix. So typically the length of an Ofdm symbol is capital T, which is basically the sum of your symbol duration plus the cyclic prefix. Okay, so from here we can conclude that Ofdm doesn't have the maximum bandwidth efficiency in practice, right? Suppose if you want to denote or calculate the bandwidth efficiency of Ofdm symbol, which is given by say eta, T symbol is the actual duration of the Ofdm symbol, whereas we are occupying T units of time. So the bandwidth efficiency is not surely 100%. It is going to, since T symbol is going to be less than your capital T because of the addition of a cyclic prefix, your bandwidth efficiency is surely going to be less than 100%. Right. To summarize, Ofdm has a lot of advantages, but its prototype filters aren't optimal for narrowband subcarrier narrowband multi-carrier communication, and in practice they do not provide the maximum bandwidth efficiency. This is where your Fbmc comes in. Basically Fbmc is targeted to solve these two problems, where you try to provide an optimal solution, optimal prototype filters for multi-carrier communication, and also achieve maximum bandwidth efficiency, right? So basically in Fbmc, a set of parallel data symbols are transmitted through a bank of modulated filters. See, from the block diagram you can again see that at the at the transmitter we use some kind of filters, right? And the main difference between Ofdm and Fbmc lays in the choice of the prototype filter. However, this selection basically depends on the modulation technique. For example, some Fbmc systems are designed to transmit complex value system, say for example QAM data symbols, and others are limited real value data symbol. Both of these methods have their roots in early development of digital communication systems, even before Ofdm, right? And Fbmcs are basically systems which are still under active research, and there are multiple ways to implement them. So to quickly compare between your cyclic prefix based Ofdm signal, system, and an Fbmc. Basically, your cyclic prefix based Ofdm is certainly the most researched and popular type of multi-carrier communication systems, wherein your channel estimation and equalizations become trivial task. Why? We have high performance digital signal processors available, which takes care of the task of equalization and channel estimation. And with the insertion of some redundancy, basically your cyclic prefix, the frequency selective propagation channel becomes a frequency flat subchannel, right? The major disadvantage of Ofdm when compared to other multi-carrier modulation schemes is loss of spectral efficiency due to cyclic prefix insertion, higher out of band radiating, and higher sensitivity to narrowband interferers, right? Fbmc basically have their roots in the pioneering work of Cheng and Salberg. The references are given at the end, who basically introduced multi-carrier techniques almost 2 decades before the introduction and application of Ofdm. A general overview of your Fbmc system is shown in the figure. It can be basically considered as an evolved form of your Ofdm. The filter banks address the main disadvantages of Ofdm mentioned above. One of the main disadvantages, spectral efficiency. First, their subchannels can be optimally designed in the frequency domain to have desired spectral containment. And second thing is FBMC systems basically do not require redundant cyclic prefix and are basically more efficient spectrally.